Hello everyone, in this video you'll be learning about the softmax and the cross-entropy loss function. This is the third video of the above playlist. In the first video, we've learned how to create our own CNN model, and in the second video, we've used the large pre-trained model to fine-tune it on our target domain dataset, and in this video, we'll get a fleeting acquaintance with some mathematics used so far, which are cross-entropy and the softmax. The Formula 1 and 2 show the cross-entropy and the softmax functions respectively. The cross-entropy loss is defined as in Formula 1. N is the number of total samples, M is the number of categories, Yi indicates the ith element of ground truth vector, Y hat I is the ith element of the predicted vector. So let's look at an example. Given an input facial image, then the model predicts the corresponding emotion, and y hat is the predicted vector, and y is the ground truth vector. And in this case, the position 1 is set to 1 and the rest of them set to 0 because the ground truth is happy for the given happy face. And if we calculate the cross entropy function for between these two vectors, then let's take this part first. Then m is 3 because we assume we have got a model that determines one of 3 emotion categories: happy, neutral, and sad. So y1 times log of y hat 1 plus y2 times log of y2 hat, and y3 times log of y hat 3. y3 is the third element of the ground truth vector, which is 0, and hat y3 is the third element of the predicted vector. So if we assign the values for each symbol, 1 times log to the base e of 0.7, and for this log function, we assume that it has base e, so y1 is the first element of the predicted vector, so 1 times log to the base e of actually y1 is the first element, one's element of the predicted vector, so 1 times log to the base e of one's element of the predicted vector 0.7 plus 0 times log to the base e of 0.1 plus 0 times log to the base e of 0.2. See that y3 has 3 element in the predicted vector is 0.2. Anyhow, these two become 0, and we get minus 0.357. And if you see, we have got minus sign here, so if we take it, then we get positive value of the loss value 0.357. And see that the model predicted correctly because it is giving the highest probability for the happy emotion. And let's look at another example for the second sample. Then this loss value is a lot higher compared to the earlier sample, and it is because the model mispredicted, giving the probability of neutral the highest for the given happy face. The actual emotion for this image was happy, but the model predicted wrong, incorrectly. It predicted it as neutral. So the purpose of training the model is to minimize the loss value, which means that we are trying to have the distribution of vectors as close to the ground truth vector, as close as to the ground truth vector. So otherwise, the loss is going to increase, then it means something is going wrong for the training. So for let's fill in the rest of them, and for the last set phase 2, we get 0.511 for the loss value. So this time for the set phase, the it predicted it correct. It's giving 60% of percent of the input image being the sad emotion, and the ground truth is sad. So this time 0.511 is low. So the higher the probability to the true emotion category, the loss is going to be lower. So taking this one, we add up all the samples, all the loss values for each sample. Then we add up all this and divide by 5. And remember that we have already taken minus sign. So it's gonna give 0.746 for the for these samples, for the cross entropy function. So this is the output of the cross entropy function for these 5 samples. So the left figure shows the distribution before training, and through the training process, the intra-class points cluster together. So the right figure shows the feature distribution after training, and this process is called as learning feature representation. The better feature you learn, the better the model performs. The goal of learning feature representation is to have large interclass variance and compact intraclass variations. So what I mean by large interclass variance is that the points that belong to different categories. In this example, the red point and blue point should be far apart from each other, and those points that belong to the same category, for example, these blue points should be close to each other. So let's practice how to visualize the learned features in Google Colab. And if the intra-class points cluster together, that means the training process is going well. And you can get my code repository, and if we go to the link, then you can get the code, and let's download. um, let's remove this and let's name it feature disk, and let's go to Google Drive, and I've got this folder, and let's go to this folder, and let's drag this and drop here. My drive, and double click this. Let's try again. I guess we have to wait because the loading is still going on. Let's stop this and let's go to let's remove one file and let's go to my drive, and in dataset folder I've got sad and happy folder, and in sad I've got sad images, and back in happy folder I've got happy faces. And let's go to my drive again and let's go to viz and double click, open the notebook, and check your runtime type is GPU for fast training. And let's mount run again. As I have seen earlier, the root path is set to the directory where we have the facial images. Connect to Google Drive. Um, Down. Um, Something's wrong. Let's run again. Um, Continue. So it's um it's done, and run again. Run. Um, Dataset. Let's check our drive, my drive, and in dataset I've got happy and sad, so I haven't got FAR folder. Close. And let's check how many items for happy. We've got 1481, and how many sad? We've got 1247. So let's make it undo it, and let's keep running. So we define resonance 50 here, and say that we haven't applied softmax, and let's compile. And what model the fit does is that it does the training, but without training, let's first observe the how it predicts the distribution of the predicted vectors, and run again. Um, let's wait a bit until it runs. It finishes running. So once the training has finished, and if we plot the feature, if we plot the predicted vectors, then we can see these predicted vectors are randomly distributed. And if we go up, because we get test accuracy of 45%, and it is because, as you can see on the plot, we cannot discriminate these predicted vectors. So as I mentioned earlier, through the training, we are trying to um, have the points, the intra-class points closer to each other. So if let's go up and let's uncomment this, and this time model.fit, and it's going to train, and you can see we pass model checkpoint callback for the callbacks parameter, and if we go up, model checkpoint callback is assigned with the file path, model save path. So model save path is the join of the save directory and the save model name. And as you can see, save model name, we have epoch and the validation loss. It is named as epoch and the validation loss. And if you go to the official documentation of Keras for model checkpoint, you can see file path parameter, and if we go down, then the file path is, if a file path is Apple, here's explanation about the argument, and if a file path is Apple O2D minus validation loss colon dot to f dot keras, then the model checkpoints will be saved with the epoch number and the validation loss in the file name. So the weights is going to be saved with the name, epoch number, and the validation loss. So the directory where these files are saved in my drive and save the models. So if we open save the models, then we get the saved weights. And now what we gotta do, we gotta load the weights. So we are going to load the last save the model, save the weights. So it's epoch 10. Once the epoch 10 finishes, we are going to have epoch 10 checkpoint named with epoch, number epoch, and the validation loss. So we've got epoch 10. For epoch 10, validation loss is 7.607. So it is 10-7.61. So 10-7.61, and we need to load the weights by calling model.loadWeights of saved model path, and run. Let's validate. Let's use another loss for because this one shows the higher validation accuracy, and it is validation loss 4.004. Let's close this, and validation accuracy 0.75 is at epoch 8, and let's use epoch 8, epoch 08 dash 4.004.00. Then we get the test accuracy 73%. And if we plot again, we've got prediction list, and for each sample, the model predicts, and we save it in prediction list. And as you remember, because the train y, the label is one hot encoded, so we get the index of the true label, save it in Scala label. And actually we don't need this part. Let's remove this. So what we gotta do, um, let's run this again. We are adding the predicted vector to prediction list, and down here, once it finishes, let's run this. The label colors are set to blue and red. For happy emotion, it is set to blue, and for sad emotion, it is set to red. Let's rename the title as feature distribution after training. And for each prediction, we scatter plot zero element and the second unit and the first unit. And remember, we pass 0, 1 for the index because the index starts from 0. And the label colors, and we get the um, index of the true label to fetch the corresponding color for the given label. So let's wait a bit and let's look at the distribution of the predicted vector. Let's wait a bit till it finishes. So if we look at this distribution of the predicted vectors after training, and it somehow we can discriminate um, compared to the distribution without training. And now because we can discriminate these two different features, we can have the test accuracy of 73%. So if we go up, as you can see, when we selected the epoch 10, the weight of epoch 10, we see that the validation loss is 7.60. And if you remember that we got low test accuracy for this by using these weights. And because the overfitting has happened, so train accuracy um, uh, actually not overfitting, but um, this one validation loss. So you need to select the lowest validation loss to have higher accuracy. So because this one epoch 8 had validation loss lower than this epoch 10, we could get higher accuracy. So to have the best validation loss, you can set if we go up in model checkpoint, you can set save best only to true, then it's gonna save the best loss, the weights for having the best loss. So now we've seen how what happens when we train the model for the predicted vectors, and if we go up, then what we get for the validation loss and these loss values is the output of the cross entropy. And where we define the cross entropy is here. When we compile, then we by passing binary cross entropy, we compute the loss value with this cross-entropy function. And let's go up, and next let's look at the softmax. And going back to the slide, so softmax, to be simple, scales the output units to range from 0 to 1. So why we do that is because it's easier to find the discriminative distribution within certain boundaries rather than unlimited boundaries. So if you look at the plot, it the range, there's no limit, so it is quite hard for the model to find discriminative distribution. But if we scale it to range from 0 to 1, it is the model finds it easier to find the discriminative distribution. So the for the input vector z, if we take a sigmoid, then the ith element for the output of the sigmoid is e to the z1, and z1 is 3, so e to the 3 over the sum of all the e to the z I, so e to the z3 plus e to the minus 1 plus e to the 2. So if we calculate, then it's gonna give us these values, and you can see that these values without boundaries are scaled to range from 0 to 1 um, as probabilities for each category. So we can see that um, in going back to our collab, we can see the values by printing out the predictions. So if we plot pred 0 and run, see 2.42 minus 0.58 minus 2.61 minus 0.70. So these are the logits, and if we take softmax, then these values are going to be scaled through from 0 to 1. So if we go up, and if we take x softmax, let's run again with softmax. After the logit, the output of logit is passed to softmax, and the output, see, for the outputs is going to have the output of the softmax. So run and run again bit, and let's check once the training finishes. Let's rerun this, and let's train again, and let's run this cell once the training finishes. So as you can see, the validation accuracy is pretty high for even for first epoch. So you can see that when we have set a boundary from 0 to 1, the model can converge faster. What I mean by it can converge faster is that it can minimize the loss towards 0 um, faster than um, not having the boundaries. So once it finishes, once the training finishes, let's check again. Let's use the model weights saved at epoch 10, and the name is going to be epoch 10 validation loss 0.63. So if we go down 10, we have it's not yet finished, so we can see, we'll be able to see the saved weights once the training finishes. Uh, let's refresh. Oh, saved models down here 10, so we can see validation loss 0.63 for epoch 10. So let's pass epoch 10 for 0.63, that checkpoint, and if we run, then the test accuracy we can get 88% roughly, which is pretty good. And this time if we run this, then we can see that these the elements of the predicted vectors are ranging from 0 to 1. So this one uh, are quite hard to read because they have many precisions, but anyhow, you can see that they are ranging from 0 to 1. So um, for today, we've learned about cross-entropy loss function and the softmax function, and um, the result of taking softmax and the effects of minimizing the loss values using the cross-entropy function. So I'll finish off here. Thanks for listening. Goodbye.